In this video, we'll continue our discussion of derivatives, partial derivatives, by doing some more examples. Okay, so the first thing we're going to find, we have y to the negative x, and we need to find the partial of f with respect to x. Okay, so we're treating y as the constant here. Now, I don't know if you remember these rules, but we do have, let me write this up here, the derivative of, okay, let's write this down correctly. A to the x is equal to ln of a times a to the x. Okay, so we're doing this with respect to x, so the variable is x, while y is a constant, so we can use this rule. It's a chain rule. So we get ln of something, whatever the something is, so we get ln of negative x times y to the negative x. No, I lied to you guys. This is a y. There we go. Now we're following the rule correctly. Times negative 1, because that's a chain rule. So this is equal to negative ln of y times y to the negative x. That's using that rule up there. All right, so that's our partial with respect to x. Let's now do our partial with respect to y. So y now, the negative x is a constant. This is going to be a little weird. It's just a power rule. The negative x comes down, and then I subtract 1 from the power. So the partial with respect to y is negative x, y to the, I think this looks cleaner, but you don't have to do it. Factoring out the negative. All right, kind of strange. We got to get used to the partial idea of leaving constant one, the other one constant. So we're going to be using our table and identifying, like in this problem, the rule that we had here, that a was the constant. So it made sense to let this y be the constant when our derivative is with respect to x. Okay, this next one I'm giving you guys, anything like this I would give in a table. These are hyperbolic trig functions on this next example. Hyperbolic geometry is geometry done on a disk. It is it gets different in 3 space and stuff. There's actually a lot of talk about this hyperbolic geometry at the moment when it comes to astronomy, or I guess astronomy would be the wrong word, I guess, there, but maybe cosmology, the beginning of everything, and just kind of that study. There are current astronomers that believe, or astrophysicists that believe, that we are in a black hole. And that explains the speed of light. I'll let you think about that because I'm just kind of talking out of videos. But this hyperbolic trigonometry is very interesting once you get to a certain point. Like I said, any of these weird derivatives, I'm going to give you a table. You'll be fine. Okay, so we're following that rule, and they want us to find the partial with respect to both. So I got z to the x. Now notice that x is in this term and in that one, which means I got to do a product rule. So I'm going to write this out to help us not mess it up. Partial with respect to x of hyperbolic sine of x over y. Cool. Okay, so this is equal to the derivative of x squared is 2x hyperbolic sine x over y. Plus, okay, I keep my x squared, and the derivative of hyperbolic sine of something is hyperbolic cosine of the same thing, and then we got to times by the derivative with respect to x on the inside. Now this is a little weird. If I rewrite this as 1 over y times x, remember y is a constant, so the derivative here with respect to x, okay, well let's think about it. If it was a constant in some other way, it'd be 3. So this is 1 over y. That constant is the y, so we get that derivative. So we get a 1 over y. I think I'm going to leave that one alone. That looks great to me. I'm going to shrink this and move it to the side. Sorry if you used up your note room. All right, there's one of them. That's the partial with respect to x. They also want the partial with respect to y, which is actually a little shorter. The only y is inside. So x squared is a constant. I leave it there. The derivative of hyperbolic sine is hyperbolic cosine. I guess we should have put x's up here. hyperbolic cosine, I keep the inside, and then I take the derivative of the inside. This is a constant over y, so we actually get negative x over y squared. I'll let you do that derivative if you need. Remember, the x is just a constant. Right? And I think that's a great answer for the partial with respect to y. We could move things around, I guess so. We got negative x cubed over y times hyperbolic cosine of x over y. Sure, it looks a little cleaner. All right, so that's how we deal with those. I'm trying to give you a bit of every type of function, working with the table, stuff like that. So again, practice, practice, practice. This is going to take a while to undevelop habits that you've made with normal functions. And you got to be able to do both. So, okay, so we have this now. Notice that we have x, y, and z. It's the same, but I can find a partial with each one. So the partial of w with respect to x, all I got to do is pay attention to the x's. I got 3x squared. Minus 4xy, I got minus 4, and the y is constant too, so I keep that. This with respect to x is 0. This with respect to x is also 0. So there's wx. Let's do wy now. This does not have a y in it, so it's 0. The next one is negative 4xy, so the constant is negative 4x in that case. The next one, I have a yz squared. The constant in that case is z squared. And then this last thing has only a z, so that's also 0. All right, we got one more. W with respect to z. All right, there's no z here, so that's 0. There's no z here, so that's 0. So the first one is 2yz. And then the last one has only z, so it's a normal derivative. So we can add more variables and take more derivatives. This would be great in applications. The more variables that we have affecting some kind of measurement, we actually can find what the change in that variable looks like. How does that affect the overall measurement? How does x affect w? How does y affect w? And so on. Like, this is going to allow for a lot of applications. And we'll see one in a moment. All right, now we have x, y, z, and w. And we're only going to do a few of these. I'm not going to do all 4, but we could do it 4 ways. Okay, fx. All right, it's going to take a little bit of work. Actually, this one is deceptively easy. Okay, I'm going to rewrite this whole thing as w squared over y plus sine of zw x. Notice that that is the same thing, just really bad handwriting there. But that's the same as that. Everything inside here is a constant. This is the same thing as having like 3x. So if I take my derivative, right, of 3x, I get 3. So the derivative of this thing is just going to be that blurb there. So the derivative is w squared over y plus sine of zw. Very nice. You can find that once you start looking at it, you'll see it. Hopefully you'll catch it now that I've shown you that this happens. All right, so there is my partial with respect to x. That's nice. Very, very nice. Easy to do. All right, now they want us to find the partial with respect to w. But notice that I have w on top and bottom. I am going to use the quotient rule. So the quotient rule is low d high, remember these are partials with respect to w, minus, I keep the, so low d high minus high d low. I know it's a pain to write everything out, but it actually does really help and keeps it less overwhelming. So let's put a fraction bar all the way across. And then remember, it's over the bottom squared. So y plus sine zw, sorry, all that squared. Okay, so fw, I keep the y plus sine zw, keep calling it y. Now the derivative of this, we're right here. Derivative of that with respect to w. This is going to be 2xw minus, okay, I keep my xw squared. And now I got to take the derivative of that inside with respect to y. That goes to 0. And then the derivative of sine is cosine, and this has been multiplied. Cosine ZW times the derivative of ZW with respect to W, which is going to be Z. All over that thing squared. I don't think this is going to clean up at all. So I think we should just leave it here. I think that is a great answer for that. It's messy, but it's fine. I don't think... Oh, I am missing a couple things here. That a square. I don't think it's going to clean up at all, so there's really no reason to multiply things out and try to get it to work out. And it just doesn't look like it's going to. All right, so those are partial derivatives. We're going to work our way into some higher derivatives and then work our way into implicit differentiation given a partial.